For decades, the sensory reality of mass transit in India has been defined by the heavy rumble of diesel engines, belching dark smoke into the air. That exhaust carries a massive carbon footprint and creates a real health hazard for communities alongside the tracks. But you cannot simply pull these trains offline. The Indian rail network moves over 20 million passengers every single day. Because the system is so tightly packed and interconnected, standard, localized efficiency tweaks barely make a dent in the overall emissions. This creates a severe paradox for the nation. Rapid economic expansion demands more trains, more routes, and more cargo capacity. Yet running an expanding fleet of diesel locomotives across heavily congested routes accelerates the exact ecological damage the country needs to escape. Shaving a few percentage points off fuel consumption will not solve the problem. A nation of this scale requires a complete overhaul of how it secures and consumes energy, moving entirely away from imported fossil fuels. That transition started moving from theory to reality on July 17, 2026. Prime Minister Narendra Modi flagged off a pilot project on a specific non-electrified stretch of track in Haryana, the 89-kilometer route between Jin and Sonipat. Rolling down that broad-gauge track is a custom-built train set hauling 10 passenger coaches. It operates at 75 kilometers per hour, matching standard regional transit speeds. But what makes this machine entirely different is the exhaust. Instead of a smoky diesel generator, these power cars drink in hydrogen gas and breathe out nothing but clear water vapor. This isolated 89-kilometer run is a high-stakes stress test. It is designed to prove whether India can practically build, run, and scale an entirely self-reliant green energy transit network. To understand how a multi-ton locomotive moves without burning anything, we have to look inside the power car. The process begins with a series of specialized high-pressure tanks safely storing compressed hydrogen gas. That gas flows into the core of the system, the fuel cell. Here, the hydrogen is forced to react with ordinary oxygen pulled straight from the ambient air outside the train. The two elements converge inside a central membrane. This controlled chemical reaction sparks an electrical current. That electricity is routed directly down to the motors on the wheels, driving the train forward. There is zero combustion happening anywhere in the process. Because the only ingredients are hydrogen and oxygen, the only physical byproduct of that energy exchange is H2O. Clean liquid water simply drips out of the system's exhaust. Mastering this specific chemistry at an industrial scale allows engineers to completely decouple heavy mass transit from fossil fuels. The government designed this project around the concept of Atmanirbhar, self-reliance. They refused to import foreign hydrogen trains to solve their domestic transit problems. Instead, the entire technological leap was executed domestically. Indian Railways managed the build, RDSO spearheaded research, and cars were manufactured at the Integral Coach Factory. A train needs fuel to run, so the domestic engineering had to extend beyond the tracks. They constructed a highly specialized hydrogen production and refueling plant in Haryana, just to keep this single pilot route operational. This localized infrastructure is the physical footprint of the government's National Green Hydrogen Mission, a broader strategy to control the production of next-generation power sources. The physical train proves the science works, but the domestic factories and refueling stations prove that India can engineer and sustain its own end-to-end green supply chain without relying on outside nations. Yet, technological success does not erase economic friction. The mechanics of the pilot run beautifully, but expanding this tech requires staggering upfront capital. The immediate bottleneck is the fuel itself. Producing green hydrogen, which uses renewable energy to extract the gas, is currently very expensive and faces severe scaling problems within India's resource limits. Then there is the geography. To move beyond this single 89-kilometer route, the government would have to build a highly specialized, high-pressure refueling network across one of the largest continuous rail systems on the planet. Having the capability to build a hydrogen train doesn't automatically make it economically viable. A nationwide rollout right now is a precarious, high-risk financial commitment. This creates a massive political and human hurdle. Leaders face overwhelming pressure to spend budgets on the everyday miseries of the system. Millions of voters are dealing with daily delays and overcrowded cars right now. Compared to hydrogen, there is a much safer alternative, simply expanding standard overhead track electrification to clear current transit bottlenecks. Human nature often drives operators to chase quick diesel savings or vote-friendly repair projects. It is far more difficult to patiently fund future-proof technologies that will take decades to yield a visible return on investment. That is why the Jin-Sanapat route is a perfect test case. A short, non-electrified corridor frames exactly what hydrogen power can achieve and the severe infrastructure limits currently holding it back. The technology is proven and the factories are ready. The question now is whether India can maintain the generational budget focus required to hit its net zero goals without leaving the immediate needs of everyday passengers stranded on the platform.